Welcome everyone. For our group presentation, we will explain the Kepler's law of planetary motion, specifically the third law, which is also known as the law of harmonics. So, Johannes Kepler proposed three laws to describe how planets move around the sun. So, the first law states that the planet move in an elliptical orbit with the sun at one focus. The second law states that a planet sweeps out equal areas in equal times. And then the last one is the third law, which is our focus today, states that the square of the orbital period is proportional to the cube of the semi-major axis of the orbit. So mathematically, the orbital period t squared is proportional to the semi-major axis cube, where t is the orbital period and a is the semi-major axis. So now we are going to see step by step how to derive the Kepler's third law. So, step 1. To derive the third law, we start from the Kepler's second law. The aerial velocity is given by aerial velocity equals to L over 2m, where L is the angular momentum and m is the mass of the planet. Since the angular momentum per unit mass is L equals to L over m, so we substitute L equals to ml into the equation. This gives the aerial velocity equals to L over 2. This means the rate at which area is swept up is constant. For the next step, we need to find the orbital period. Next, we integrate the aerial velocity over one complete orbit. Since dA over dt is equals to L over 2, then integrating from time 0 to t gives dA equals to L over 2t. And then we need to rearrange the equation. So we obtain t equals to 2a over L. And then this equation relates the orbital period to the total of the orbit. So for the next step is the area of an ellipse, because a planet moves in an elliptical orbit. So we use the total area is A equals to pi AB. And then we need to substitute the A equals to pi AB into T equals 2A over L. And then we got the new equation is T equals 2 pi AB over L. So since the semi-major axis B equals to square root 1 minus eccentric square A, we need to substitute the semi-major axis into the new equation we got just now. And then after the substitution, we got the last equation in the red box is t equals to 2 pi a square root 1 minus eccentric square over L. And then we need to square root both sides, and then we got the very final equation for this step in the highlight one, which is after we simplify the equation. For the step 4, we need to simplify the equation again by using the relationship alpha equals to 1 minus eccentric square A. And then we need to use the shifting method, and then we got the new equation as in the highlight. So we need to substitute the new equation into the previous equation we got from the step 3. So for the last, after the substitution, we got the last equation as in the red box is t square equals to 4 pi square a cube alpha over L square. For the last part, we will be obtaining the Kepler's third law. So, from the orbital mechanics, we know that the alpha equals to ml squared over k. And then we need to use this relationship to substitute into t squared equals 4 pi square a cube alpha over L squared. And then we do some simplifying the equation, and then we got the last equation, which is t squared equals 4 pi square a cube m over k. And then we move to the next substitution, which is the k equals to g and m. So we need to substitute again by using this equation into the equation that we got perform the previous substitution by relationship of orbital mechanics, and then we do some simplifying equation. We got the Kepler's third law final equation, which is T squared equals 4 pi squared over GMA cube. What is interesting about this result is that for planets orbiting the same central body, such as the Sun, all the other terms remain constant. Therefore, the only variables that determine the orbital motion are the orbital period, T, and the semi-major axis, A. This leads directly to the Kepler's third law, which states that T squared is proportional to the A cube.
Now, I will explain about the application of Kepler's law. Kepler's law states that the planets orbit in ellipse with the Sun at one's focus, and today this principle is vital for orbital mechanics, including the operation of International Space Station, which is ISS. It is also the technology behind our daily GPS. Now, we are moving on to Kepler's law of harmonics. This law defines the clear relationship between a planet's orbital period and its distance from the Sun. Simply put, the square root of the orbital period is proportional to the cube of the semi-major axis, as expressed by this formula. Now we are moving to the next slide, which is the daily life example for the law of harmonics. To see the law of harmonics in actions, look at the geostationary satellites. These satellites are crucial for service like weather forecasting and television broadcasting. By staying fixed at the single point in the sky relative to the ground, they ensure we receive a consistent, uninterrupted signal transmissions.
Next, in this section, I will solve the problem involving satellite motion and the Kepler third law. For part A, the question asks to show that the radius for a circular orbit of a synchronous 24-hour Earth satellite is about 6.6 Earth radii. First, we use the equation that relates to the orbital period, which is 4 pi squared A cube divided by GM, and then we arrange the period to become the subject. Next, we substitute the value, which is the gravitational is 6.67 times to the power of negative 11. Earth mass is 5.97 times 10 to the power of 34 kilogram, and the period is 86,400 seconds divided by 4 pi squared. After the calculating, we obtain the radius is 4.22 times 10 to the power 7 meter. To express the answer in Earth radii, we divide it by the Earth radius, which is 6.4 times 10 to the power of 6 meter. And the final answer is 6.6 Earth radii. For part B, the question states that the distance to the moon is 60.3 Earth radii and asks to calculate the length of the sidereal months, which is the period of moon orbit. We use Kepler's third law, which states that the square of the orbitals is proportional to the cube of the orbital radius. Substituting the given value into the equation, which is 34 divided by t squared equals to 6.6 divided by 60.3 cube. And then we move the t squared and the radius. We get 24 over 60.3 divided by 6.6, 3 over 2. And we obtain the period, which is 6 162.4 hours. Finally, we must convert hour to days by divided with 24 hours. And the final answer, we will get 27.6 days.
Kepler's law of planetary motion is a law that describes how the planets move around the Sun. All planets move around the Sun in elliptical orbits. The planets move at a different speed depending on how far they are from the Sun. The planets that are closer to the Sun move faster, and the planets move slower when they are farther from the Sun. The law shows that the planet's orbital periods and its distance from the Sun have an exact mathematical relationship. Kepler's third law shows that the square of the planetary orbital period is proportional to the cube of its semi-major axis. Kepler's first and second law describe the movement properties of a single planet, while in the third law, the astronomers make a comparison for each of the planetary motion and determines the harmonics. For the solar system, this can give us a precise representation of each planetary orbit around the Sun. The time for the planets to orbit the Sun will increase as their distance from the Sun increases. In conclusion, Kepler's law will show how the mathematical relationship can be used to understand and predict the behavior of celestial objects, constitute a significant achievement in scientific history.